Hello everyone. In this video, we are going to look at chapter 19, section 19.1 and 19.2. In this chapter, we're going to learn the formulations for linear and angular momentum of a body, and we're going to apply the principle of linear and angular impulse and momentum. Let's see, basic concept, starting with the basic concept. We learned it before. Linear momentum equals m times v, mass times velocity. Angular momentum, we use the letter h, that will be hg equals ig omega. And remember that the direction of hg is perpendicular to the plane of rotation. In translational motion, if I have something that only translating, no rotation at all, the h will be zero. So other words, this over here, the angular momentum will be zero. We only have linear momentum because I only have translational velocity. I have no omega if I'm not rotating. Now, if I'm rotating about an axis, passing through point O, the body's linear momentum and angular momentum are L equals mvg and hg equals ig omega. It is sometimes convenient to compute the angular momentum of the body about the center of rotation. So therefore, we have this h0 equals rg cross mvg plus ig omega. That will give us I0 omega. Um, if it's under general plane motion, a lot of times the rigid body is, both the linear momentum and the angular momentum can be computed about point G are required. You have L equals mvg, hg equals ig omega. Angular momentum about point A is HA equals ig omega plus mvgd. We're going to use this in our example problems today. And then the principle of sphere, as the in case of particle motion, the principle of impulse and momentum of a rigid body is developed by combining the equations of motion with kinematics. The resulting equations allow direct solution to problems involving force, velocity, and time. Linear impulse, linear momentum equation says if I have initial linear momentum plus the impulse being applied to the system, that will give me the final linear impulse. Okay, angular equation says angular impulse plus initial angular impulse plus the angular momentum being applied to the system, that will give me the final angular momentum. The previous relations can be represented graphically by drawing the impulse momentum diagram. Initial momentum plus the impulse gives me the final momentum. So give you a quick summarize. If the motion is occur in the xy plane, the linear impulse linear momentum relation can be applied to the xy directions, and the angular momentum angular impulse relation is applied about the z-axis passing through any point. This point can be G, can be any point, any other point as well. Therefore, the principal yields three scalar equation describe the plane of motion of the body. So general step, we're going to establish the XYZ in inertial frame of reference, draw the impulse momentum diagram of the body, calculate IG if needed, apply the equations of impulse and momentum, one vector and one scalar of the three scalar equations. If more than three unknowns are involved, then we're gonna need to introduce additional equations. For example, kinematic equation relating the velocity and the mass center G and the angular velocity omega should be used to furnish additional equations. Let's take a look at some examples together. We have 300 kilogram wheel has a radius of gyration about its mass center O, KO equals 0.4 meter. The wheel is subject to a couple moment of 300 Newton meter. We're looking for the angular velocity after 6 seconds after it started from rest with no slipping occurs. So basically I have momentum initial, which will be zero because we are starting front rest. Starting front rest, that means initial momentum is zero. And then plus the total, the MT, the impulse, angular impulse equals your final momentum. And then final momentum, there's angular momentum, there are two parts, right? The MVR plus IG omega. And really the rest of them, you just plug in the values of, we're using the radius gyration to help us figure out the mass moment of inertia. This number right here, radius gyration, use this zero point 0.4 to figure out the mass moment of inertia, and then really we can calculate the final angular velocity. Next example, we got two gears. The two, we know the weight, both of their weight, both of the radius gyration, and then we know how much moment is being applied to it. Moment is at gear B. That's right, our equation. We're looking for angular velocity of a gear after 5 seconds if you start from rest. Start from rest. This is the free body diagram and the kinetic diagram. Start from rest. That means my initial kinetic energy. Initial velocity equal to zero. The initial angular momentum, linear momentum, all equal to zero because it's starting at rest. And then so for gear A, we have FTRA equals IA omega A, or FT equals IA omega A divided by RA. And then for gear B, we have integral, since we have moment over a period of time, integral from T1 to T2 MDT minus FTRB equals IB omega B. Combining these two equations, you got that. So basically, also you want to notice that they are a gear, two gears with two different radius, but in contact. Okay, that means their linear velocity are the same. The velocity on the edge that are in contact. So you have RA omega A equals RB omega B. Put that into our equations using the radius gyration to help us figure out the moment of inertia, mass moment of inertia, and then really the rest of them just plug in the equations. The total moment from time t1 to t2, right, from 0 to 5 seconds, we can calculate the total angular impulse and then plug into our angular equation that will help us calculate the final the omega at the 5 seconds. Okay, that's all I want to share with you in this video. Thank you for watching. Hope you find it helpful.